All right, we're ready now for our fourth conic section lesson, and we'll be discussing hyperbolas today. And so as you can see in our objectives, we want you to be able to sketch the graph of a hyperbola given the standard form equation. And then we'll be able to, hopefully at the end of this lesson, write equations for a parabola if we're given the foci and the vertices. So let's get started. Time to time, I'll have people ask me, where do these conic sections shapes show up in real life? And so I just thought before I get into the actual meat of the lesson, I'll just show you some pictures of where you would see these show up in everyday living. Here you have gears that take on this hyperbolic shape. So you can always think of a hyperbola as two parabolas that open in opposite directions of each other. The sonic boom also takes on this hyperbolic shape. It's called the sonic boom curve, and there's just another diagram of the sonic boom curve. Nuclear reactor cooling towers, you can see this hyperbolic shape, two parabolas as it were that open up in opposite directions. So let's just get right to what you're going to be doing today with the assignment. And this is the equation for a hyperbola. Let's first of all draw some distinctions, because it is easy to confuse what we just studied with ellipses versus what we're going to study today with hyperbola. So let's draw some distinctions while we also note some similarities. So first of all, if you remember from our study in ellipses, I'll just give you a real quick review. This would be the equation for the ellipse that is wide. Notice that x is the major axis because a squared, being the bigger denominator, is below it. Also notice that for ellipses we have plus in the equation. Well, for hyperbolas we're going to have minus in the equation. Okay, so that's one huge difference between the two equations. So if you see an equation, you don't know exactly what the graph of it will be, you can tell by the equation form whether it's an ellipse, plus, or a hyperbola, which would be minus. Okay, so before we draw other distinctions between these two, let's go ahead. Here's a similarity. We do have to make the equation equal to 1 for this to be in standard form, the form that we graph from. That was true also for ellipses. So the first thing I'm going to do here is divide everything by 64. So this is a repeat of what we had to do for some of the ellipse equations. So now when you reduce, 4 over 64 would be 1/16, so that's x squared over 16 minus y squared over 4. 16 divided by 64 is 1/4, and that equals 1. Okay, so now we've got the hyperbola equation in standard form, and now to begin with, it's going to look the same as what we did when we graphed ellipses. I'm going to put positive and negative 4 square root of 16 on the x-axis. I'm going to put positive and negative 2 on the y-axis. But here, from here on, it gets very, very different than the graph of an ellipse. What we're going to do with these 4 dots for hyperbolas is we're going to make a rectangle. So I'm just going to do a dotted line to show this is called the central rectangle. I've also seen it in some textbooks called the interior rectangle. We're going to go with the word central rectangle. So for you, just like for ellipses, all of your hyperbolas are going to be having the origin as the center. So we'll work on translating these in a future lesson. So what this central rectangle does for us, it's a guide, it's a template, if you will, for allowing us to draw 2 asymptote lines. Okay, so I'm going to get my line draw tool ready to go here. So if you remember, an asymptote is a line that a graph will approach forever, but it will never actually touch. Okay, so I'm going to line these up the best I can. So what you're going to do with this central rectangle, you're going to have a ruler to be able to do this. You're going to line up these opposite corners, the corners that are diagonally across from each other, and the center. So you got 3 reference points, and then you're going to make a dotted line going through those points. And I didn't do a dotted line, so let me change that. I like to have a dotted line because this isn't technically part of our graph. It's not the actual graph of the hyperbola. It's just a guide for us to draw the graph of the hyperbola. All right, so that's pretty close, I guess. Close as I'm going to get. So you line up the 2 corners that are diagonally across in the center, and you're basically going to be making an X. And you'll have a ruler for this so you can make nice and straight lines. And those represent, again, asymptotes. So here's the deal, again, a difference that you have to remember that is so different from the way we graphed ellipses. Ellipses had a major axis and a minor axis. Well, hyperbolas, you're going to focus on the variable, numerator variable that comes first. That is so important. The fact that x comes first in this equation means that I'm only going to be crossing the x-axis with my 2 parabolas. Okay, so here's what that means, and I'll do the graph in red. So I'm going to cross through this point. Now this is called a vertex. All right, that's a similar term that we learned from ellipses, but I don't have co-vertices for hyperbolas because I'm only going to be crossing through these 2 red dots. And the reason I knew that they were going to be these and not the ones on the y-axis is, again, because x comes first in the equation. So I'm going to use the red dot and those asymptote lines, and technically I should be getting closer and closer to those asymptotes the further away I get from the vertex. I'm not going to grade you on your artistic ability, but at the same time, sometimes I get people that will draw a hyperbola and they'll just do something like this. You know, and that just tells me that they don't really understand the purpose for these dotted lines that they've drawn. So I'm not going to be too harsh, but at the same time, show me that you understand that once you go through this red dot called the vertex, you should gradually be approaching. It's like that dotted line is pulling, has some sort of pull to it that pulls the graph toward it the further away you get from the vertex. Okay, so there's the graph, and now we need to include the foci. Okay, so here's another difference than what you just learned in the previous lesson. The way we find foci for hyperbola is actually using the Pythagorean theorem. So everything is switched. When we dealt with ellipses, the equation had plus. Today, hyperbolas will have minus. The equation that we use to help us find missing parts like focal points or vertices, co-vertices, when we dealt with ellipses, that was c squared equals a squared minus b squared. So this is where practice is really going to come in handy to keep all of this information straight. All right, so you got to also change your way of thinking when it comes to hyperbolas. With ellipses, 16 would have been known as a squared because it's bigger, and 4 would have been known as b squared. Well, for hyperbolas, those denominators never switch. A squared is always first, and b squared is always second. What will switch with hyperbolas is the numerators. So again, that's completely opposite. And we switched the numerators to indicate which axis we're actually going to be hitting with our two parabolas. So I just did an example of a hyperbola where the two parabolas would open up or down, up and down. Because y comes first, then we're only going to be hitting the y-axis. So for hyperbolas, pay attention to the variable that comes first. That's very important information. That'll tell you which axis you're actually going to be hitting. Okay, so let's find out where the focal points, the foci, are. C still represents the distance from the center to the foci. So in my problem, a squared is 16 and b squared is 4. Remember, a squared is always first for hyperbolas. B squared is second. C squared is 12. And now we'll do the square root of 12 plus and minus to plot the focal points. And to the nearest tenth, that is 3.5. Okay, so remember what we talked about when we dealt with a parabola, just one of these, the foci always goes inside the mouth. Well, that's going to be true for hyperbolas. It's just that we have two parabolas, and so we got two foci to plot. And I just realized, I guess I was talking about ellipses and showing the difference, and I wrote minus here. Just remember, don't do like I just did. For hyperbolas, we're doing c squared equals a squared plus b squared. So sorry about that. Let me fix this so I don't have to redo this video. So always do c squared is a squared plus b squared for hyperbolas. And one way you remember the difference between ellipses and hyperbolas. Hyperbola equation has minus, so we use the opposite sign for finding information. Ellipses has plus, so we use the opposite sign, minus, to find missing parts. Okay. All right, now that we're back on the right track, the square root of 20 is 4.5 rounded. Okay. So we're going to put, I'll just do it in black to make it a little bit different. So we have a foci there inside the mouth and there, real close to the vertices. All right, so we went plus and minus 5. So I'll call the focal points in ordered pair plus minus 4.5. Sorry. So the focal points in ordered pair form would be plus minus 4.5, 0. Okay, so terminology. We have vertices, which our graph will go through. So if we were talking about listing or giving the coordinates of the vertices, that would be plus minus 4, 0. We have foci. We've already talked about how we plot those. And then we talked about this rectangle, the central rectangle that is used to help us draw the asymptotes. And then there's one more term that you're going to need to know when it comes to hyperbolas. And it's this line that will always connect, it'll always go between the two vertices, and I'm highlighting it in green here. So sometimes you will get information like this. The transverse axis is horizontal and it's a certain length. So what they're saying when giving you the transverse axis related to a hyperbola is that segment that connects the two vertices. Okay. And with it being horizontal, anytime you're told the transverse axis is horizontal, that's just another way of saying your hyperbola is going to be two parabolas that open left and right. They'll open basically at the end of the transverse axis. If you were told the transverse axis is vertical, then that tells you that your hyperbola is going to be two parabolas that open up and down. So the length of the transverse axis, remember if A, which it is, A is the distance from the center to the vertices. So in this case, A is 4. It's 4 units from the center to each vertex. The length of the transverse axis will be 2 times whatever A is. So A is 4, so it should be 8 units from one vertex to the other, covering the distance of that green segment called the transverse axis. All right, now that we've laid some groundwork, let's go ahead and do a few more, and then you'll be ready to attack the assignment. So here I have y squared comes first. So that tells me that when I'm done graphing, I should have 2 parabolas roughly that should do this with a vertical transverse axis. Y comes first. I'm only hitting the y-axis with my 2 parabolas. All right, so let's make the central rectangle. So I'm going to put positive and negative 4 on the y-axis. And I'm going to put positive and negative 3 on the x-axis. So remember, in hyperbola equations, the first denominator is always a squared. Second is always b squared. Those never change. So when you're writing the equation for a hyperbola, you can always do this. This never changes. What you will alternate, depending on the graph, is where you put x squared and y squared. All right, so let's go ahead and make a rectangle out of these 4 points. And we'll grab a ruler and line up the center, the origin, and these corners that are alternate from each other. So I'll just see if I can line those up with my line draw tool. All right, so there's an asymptote. There's an asymptote. I missed this corner a little bit, but I think you get it. I should have gone through that corner, through the middle. So with your ruler, it's pretty easy. Not so easy with this board, but just line those up, 3 points, the 2 corners and the center, and then you'll have it. So those are asymptotes. Now I'm going to draw the graph, and again, since y comes first in the equation, I'm only hitting the y-axis, so these blue dots are the vertices. All right, so just show that once you pass, eventually you're going to get closer and closer to those 2 asymptotes, but you'll actually never touch them. Something like this. All right, and now we'll find the focal points. So c squared is a squared plus b squared. A squared is 16. B squared is 9. So this one's nice. We don't have to deal with a fraction. So it's 5 units from the center, origin, to the 2 focal points, and we need to put those inside the mouth. So let's do those in a different color. So I have a focal point at 0, 5, and 0, negative 5. Those are the foci. All right, looks like we got the graph. Just want to highlight when you see that lead variable, that's big information on how the parabolas should look. All right, that's the answer when we do these in class. I'm going to have the students try them on their own and then see if they got it right. So now let's work on writing some equations. So here we're told to find the equation of a parabola that has one focus located at 4, 0 and one vertex located at -2, 0. Okay, so The center, of course, is at the origin. That's going to be true for all of your hyperbolas. So we can go ahead and identify A as 2. A is the distance from the center to the vertices. So we have a vertex located here. That means obviously we have another one located at 2, 0. All right, we can also label C, which is always the distance from the center to the foci. C will be 4. So we got a focus at 4, 0. We'll have another one at, of course, negative 4, 0. So again, when you're writing the equation for a hyperbola, everything's flipped. You can go ahead and write down a squared and b squared in these places. A squared is the first denominator. So since we know what a is, we know what a squared is. What we don't know is b squared, but we can find it very quickly by using the Pythagorean theorem. All right, so c squared is a squared, and we can solve for b squared. Subtract 4 from both sides, and we got b squared is 12. Okay, now pay attention to the axis that the focal points and the vertex are on. They will always, for a hyperbola, be on the same axis, and they're both on the x-axis. So that means the graph, if this were graphed, it would only touch the x-axis at these two vertices. So that means in my equation form, I'm going to lead with x squared. You lead with the variable that the graphs are actually touching. You're only going to be touching one graph, or I'm sorry, one axis with your two parabolas. So there's your answer for number 4. Let's try another one. This time we're told the vertices are and the foci are on the y-axis. All right, so we can go ahead in this case and we can say y squared, x squared. We also know that a is the distance from the center to the vertices, so a is 3. C is 5. So I can go ahead and put 9 here because in hyperbola equations, a squared is always first. So once again, we're going to have to solve for b squared. Pythagorean theorem. So 25 is equal to 9 plus b squared. Subtract 9 from both sides. B squared is 16. And there's your equation. All right. Another example. Let's write the equation for this hyperbola. All right, so we can go ahead and set it up. Notice the axis that the foci and the vertices are on. They're on the y-axis, so that means my hyperbola is going to be two parabolas opening up and down on the y-axis. Okay. I know that a is 2, so a squared is 4. So again, kind of like what we did before, let's find b squared. So c squared is a squared plus b squared. B squared is 12, and y should lead because we're crossing only the y-axis. And there's your equation for this hyperbola. I'm going to throw one more in because it's very much like your number 32 on the assignment. So the way it's worded is a little bit confusing to some people, but what they put here is this long phrase in the parentheses: the distance from the center of a hyperbola to a focus squared is 45. Okay, well, another way of saying the distance from the center of a hyperbola to a focus is, that's c. All right, so c squared is 45. All right, what else do we know? The endpoints of the transverse axis are at negative root 5 and positive root 5. Well, if you recall, and notice how these are both on the x-axis, the endpoints of the transverse axis are also known as vertices. So in rough sketch form, we're talking about a graph that would have two parabolas that do this. All right. So in other words, A is the square root of 5. Okay, so this is just good to help you really get familiar with what these terms represent. You'll see them pop up from time to time. So it's from the center to each of the vertices is another way of saying by telling you that the endpoints of the transverse axis. Well, that means that these points are the vertices, which A represents the distance from the center to a vertex. All right, so we have c squared is 45. Well, if A is the square root of 5, then A squared is 5. Okay, and now all we need is we need B squared to finalize the equation. So c squared is A squared plus B squared. So B squared is going to be 40. Now we're ready to write the equation. All right, so A squared is always the first denominator. B squared is the second denominator. And by virtue of the fact that the transverse axis is horizontal, also knowing that the vertices are on the x-axis, that means that x squared is going to lead and y squared will follow. And there's your answer for this example. So when you do number 32 in your assignment, if you forget or if you struggle a little bit, you can go back and look at this. And it's very much like it, very similar. All right, I think that's it. That's the notes for this lesson. I think you're ready to do some practice problems. If you have any questions about this, please let me know.